Okay, so this is the last part of exponential functions that we're going to look at, and this is where we solve logarithmic equations. So we're going to encounter a lot of different types of logarithmic equations, and we're just going to work through a bunch of them and see exactly what we can do. So we're going to start with the most basic exponential equation that we've seen. The most basic being something along the lines of 3 to the t power is equal to 243. Okay. Now typically what we do is we use logarithms to solve, and the whole point of logs is to solve for the exponent. So let's write that down again because it is super important and kind of our goal in everything that we do. So the purpose of a log to solve for the exponent. And we said that in a case like this, it's not possible to find another way to solve it. We can't raise everything to the 1 over t power because then we may not have a t as the power over here anymore, but now it's going to have a power of 1 over t on this side. So that's not going to work. So we have to find another way. And we said that we could take this and put it in logarithmic form, which is what we did in the previous lecture when we had b to the x equals y and we needed to solve for y. Well, here we need to solve for t. So if we go back to what we did in the last lecture, we said, okay, let's put this in logarithmic form. So we get t. The base of the exponential is the same as the base of the logarithmic. And then our argument is the same thing as our answer. Now there's a problem here though. If we go to our calculator and we take a look at our calculator, we see a log here, but we don't see any base. And it turns out that most calculators will not allow you to solve a logarithmic equation with anything other than base 10, because this is a log without a base, or base e. Okay, it has a ln here, so we can use base e. But here, this is base 3, so we can't plug this in the way that it is, which means we can't solve it this way. 243 is not a power of 3, so we can't just go through and say, okay, let's do 3 to the first. Clearly it's not 3 to the first. 3 squared, we know it's not 3 squared. Even 3 cubed, we know it's not 3 cubed. But let's say we're not sure what 3 to the 4th is. 3 to the 4th is only 81. Let's try 3 to the 5th. 3 to the 5th is actually 243. So here we can do it with brute force, but this could actually take a long time, okay? And it's not the most efficient method because we have to go through, and you saw we had to do 3 to the 4th and 3 to the 5th. So let's find another way of doing this, okay? And it turns out that what we can do is we can take the log of both sides, okay? As long as we're doing it to both sides, we're okay. So we can take the log of 3 to the t power and the log of 243. Okay, this is another way of solving it other than just brute force, figuring out what 3 to the 4th is, what 3 to the 5th is. So what we're doing is we're taking the log of both sides. Now the next thing that we could use is the property of logarithms, the power property, right? And the power property says, hey, we could take an exponent and we can move it out to the front and make it a coefficient. So let's do that. So what this is going to give us is t log 3 is equal to the log of 243. And that would be our second step in these problems, is to take the exponent and move it into a coefficient. And notice what is happening here. We're using that second rule, that power property of logarithms, to help us. So this is that rule where you have, I just want to make sure I'm using the same letters. This was the log base b of x to the m is equal to m log base b of x. So we took the exponent and we moved it out to the front. And this is what makes logs special, because this particular power property allows us to get rid of those exponents, and that's what we're solving for. We can't solve for t as long as it's an exponent. And this right here, moving that t to the front, allows us to get it out of the exponent. And now the solving is pretty straightforward, because all we have to do is divide both sides by the log of 3. And that's our last step, isolate the variable. The log of 3 is going to cancel on this side. And now we could go into our calculator and we can solve. So in some calculators, you have to type in the number first, and then you press log. In this particular one, and I think in the TI-30X, you could just type log and then the number. So this one would be log, sorry. No, maybe this one we have to do it the other way. Okay, so this is one of the ones where we have to type in the number first and then we press log. So we want the log of 243. So we type in 243 and then we press log. I think on the TI-30X you don't have to do that. You would type in log 243. You have to check, okay? So we have log of 243, and then we're going to divide by, and I would do this in parentheses, okay? Parentheses, 3 log. And what we get is 5. And so we solve for t that way. Okay. Let's try another one. Let's say that we had, so I'm going to put a 1 over here. Let's say that we have 6 to the x is equal to 98. And this one I know it's not a power. So if we try it using our brute force method, if we start with 6 squared, most of you I hope know right away that that's 36. But some of you may not know what 6 cubed is. So if we try 6 cubed, well, 6 cubed is 216. So 6 to the x equals 98. That x is somewhere between a 2 and a 3. A 2 is too low, a 3 is too high. So that means that x is a decimal. So we can't really solve it using this brute force method. It would take a really long time. So we're going to use this other method where we take the log of both sides. Now we can turn it into logarithmic form. If we turn it into logarithmic form, it's x equals log base 6 of 98. But we're going to run into the same trouble where we can't put that into our calculator because our calculator will only calculate base 10. So we're going to take the log of both sides instead. I'm going to try and use different colors as much as I can just to show you what's happening in each step. So we're taking the log of both sides, and we can do that as long as we're doing it to both sides so that we're not changing the value of the equation. so this is the difference between the top equation and the bottom equation. We haven't changed anything about the equation. It's still equal. Now we can move this x out to the front. So again, here, we take the log of both sides. Then we move the x into a coefficient. The x is the exponent here. Our final step is going to be to isolate that variable because we're solving for x. Okay, so our variable in this particular one is x. So let's rewrite this. This becomes x log 6 is equal to x log 98. And then we can divide both sides by log of 6 to isolate the x. Sorry, there is no x here. I apologize for that. So we divide both sides by the log of 6. Log of 6 cancels, and now we're going to go and we're going to calculate what x is equal to. So we're going to go to our calculator. Now remember, on this calculator we have to type the 6 first. So we type in 6 and then we press our log button. And then we're going to divide. And again, I would encourage you to put, I did this in the wrong order, I'm sorry. We're going to do 98. It's log 98 over log of 6. So we're going to do the log of 98. And then I encourage you to put the denominator in parentheses. So we do divided by parenthesis log 6. And then we just press equals, and we get 2.56, round to the nearest hundredth. And that's it. So, and this kind of makes sense, okay? We did get 2.96, right? 2.56. Did seem a little high. Okay, it seemed a little high. The reason why I checked is that I saw that 6 to the 3rd was somewhere in the 200s. So it didn't really make sense that this would be very close to 3. It made more, so that's why I went back and I checked. So it's 2.56. So again, the reason why I don't go back and like rewrite the video, record over it when I make a mistake like that, is I want you to see how I know when I make a mistake. So I knew that I made a mistake because we had calculated 6 to the 3rd. And we saw that 6 to the 3rd was 216. So it didn't make sense that 6 to the 2.96 was only a 98. So that's why I went back and I checked, and I saw that it wasn't 2.96, it was 2.56, which makes a lot more sense. Let's try another one just like this, and then we'll do something a little bit different. Okay, this one I'm going to add in one small change. We're going to do 2 times 8 to the m. Notice I'm using whatever variable I want for an exponent. It doesn't matter. So 2 times 8 to the m is equal to 942. So this gives us a new first step. This is something that we haven't had to deal with before. Now we have this times 2 here, okay? So we have an exponential function. We have this x, this exponential part here, which is the 8 to the m. But now we have a times 2, and we didn't have that with the previous 2 problems. So this is not unlike everything else that we've done in the past. We have a new first step that we have to take here. We have to isolate the exponential function, okay? So we have to isolate the 8 to the m in order to take the log of both sides. And the reason for that is if we took the log of both sides here, we can't we can't move the m out to the front. And the reason why we can't move to the m out to the front is it only applies to the 8. Okay, so I'll put a little note in here that says that we would have to first separate the log of 2 times 8 to the m into the log of 2 plus the log of 8 to the m, and then we could move the m out to the front, but that's going to make so much more work for us. Okay, so I'm not even going to show you what it would look like if we did that, but I will mention it here that we have to be careful. So our first step here is to isolate the exponential function. Because only 8 is being raised to m. So the log of 2 times 8 to the m is not equal to m times the log of 2 times 8. Okay, and I'm going to put this in parentheses. This is not equal. You can't move the m out to the front if it only applies to the 8. Okay? What this is equal to this would be equal to the log of 2 plus the log of 8 to the m. And then you would be able to move this m out to the front. Okay, but here you see that then you have 2 logs. It's not that you can't solve it. You can absolutely solve it. It's just that it's a lot messier. There's no reason. You would have multiple logs instead of just one on each side. So our first step is going to actually be to divide by this 2. Remember, order of operations, the exponent comes first, so this does not become 16 to the m. Okay, the 2 cancels. What we're left with here is 8 to the m. And let's go and do 942 divided by 2. That gives us 471. And now we would take the log of both sides. So once we isolate the exponential function, everything else remains the same. So we're going to put a log in the front here and a log in the front here. So it's log of 8 to the m equals log of 471. And now we're going to move the m out to the front just like we did in the others. Move the exponent into a coefficient, we're also saying move the exponent to the front. All of this means the same thing. I'm saying it in different ways just so that you get accustomed to different terminology. So this gives us m times the log of 8 is equal to the log of 471. And then we can divide both sides by the log of 8. So we're just isolating that variable. And if we do this, again, we can go to our calculator. The log of 471 over the log of 8. So we type in 471 and then log divided by and then we're going to use parentheses, 8 log. You don't really need the parentheses because the order of operations will say do log first, but I put them in there just so that I'm comfortable with the way that it's being done, and I don't have to worry that I messed up the order of operations in any way. So this gives me 2.96. Okay, notice I'm rounding pretty typically to the nearest hundredth. I would do that unless it says otherwise. And that's our final answer there. Okay, and what this does is it kind of gives us a rule for converting from one base to another. Okay, so let's go back and just look at converting between bases, and then we're going to do other types of equations that are similar. It's just that we're going to have an exponential function on both sides. But let's first just, this tells us how to convert from one base to another. So let's say, for example, that we have log base b of x is equal to y, or y equals log base b of x. Okay, and we want to convert to base 10. Because we can't solve unless it's in base 10. Okay, or base e. So if we want to convert to base 10, the first thing that we're going to do is we're going to put it in exponential form. So in exponential form, this becomes b to the y is equal to x. And we know that the next thing that we can do here is we could take the log of both sides, because the whole idea is to solve for y. So this is just a different, we want y to equal something in base 10. Right now it's in base b. So we're going to take the log of both sides, and I'll write down these steps. But it's just like before. Okay, this is just like what we did on the previous page, where we had t equals log base 3 of 243. We had it in exponential form instead, and we took the log of both sides. So this is no different, okay? We're doing the same thing. And then the next step that we did is we took the exponent and moved it out to the front. So that's what we're going to do here. We're going to take this exponent y and move it out to the front. And then we isolate. So we divide both sides by the log of b. And the log of b cancels here. So in base 10, log base x, log of x over log of b. That's what log base b of x is in base 10. And in fact, we took the log of both sides, but we could have taken the ln of both sides. And if we took the ln of both sides instead, which is absolutely fine, then we would have y times the ln of b equals the ln of x divided by the ln of b over the ln of b. So this would actually also be equal to the ln of x over the ln of b. And if we wanted to, we could even convert to a different base. We don't have to, so we convert to base 10 or we convert to base e. And the reason for that is that that is what our calculator will allow us to do. But if instead we wanted to convert to base a, then we would take log base a of both sides, which means that we would have log base a of x over log base a of b. So we can convert to any base this way. This is what log base b of x is in base 10. This is what it is in base e. And this is what it is in base a. So our first step was to convert to exponential form. Then we took the log of both sides. But we can use any base. Meaning, if we want to convert to base A, we would take log base A of both sides. And then the rest of this is exactly what we did before. We moved the exponent out to the front, okay? And then we divided both sides by the log of b so that we could isolate the y. And both of these are equal to y, so they're both equal to each other, right? Log base b of x is equal to y. Log x over log b is equal to y. So that means if we want to convert log base 6 of 10, I probably shouldn't, let's use 11 just so that it doesn't get confusing. Because we're converting to base 10. Log base 6 of 11 is equal to log 11 over log 6. You don't have to go through this whole process every time because we went through the process, okay? If we want to convert log base 8 of 15 to base e, well, log base 8 of 15 is just ln of 15 over ln of 8. So if we wanted to convert it to base 20, it would be log base 20 of 15 over log base 20 of 8. So we can convert to any base that we want, and we don't have to go through this whole process every time, but it does show you how it works, okay, and why it works. So this is converting between bases. Okay, so let's take another type of equation, and we're going to do a few of these, and there are actually multiple ways to solve the next set of equations. And in some cases, there's one method is significantly easier than the other. So these are equations that only have exponential functions. After this, we'll look at some equations that also have logarithmic functions. Sorry, I just want to make sure that this is actually recording, so sometimes the recorder stops in the middle, and then I start talking and I don't realize it stopped, and then I have to redo like 20 minutes of video. So it seems like it's recording. Okay, so more equations. Let's take the example of 3 to the x minus 2 is equal to 3 to the 2x plus 3. Okay, and We'll put a 1 here as this is the first type of equation. Okay, so here the bases are the same. And if the bases are the same, the exponents have to be the same, okay? Because we can't have 3 to the 5th equals 3 to the 4th. That wouldn't make sense. The only way that the left side is equal to the right side is if the exponents are equal. So if the bases are the same, the exponents must be the same. And this is by far the easiest way to solve this. So there's no reason to try and solve it in any other way. Because now we just have this really straightforward linear equation, which we should all be very comfortable solving. And in order to solve this linear equation, again, some of you solve it in lots of different ways. I don't care how you solve it, as long as you wind up with your variables on one side, your constants on the other, and you get an x, okay? So here, we can subtract x from both sides. And we can actually, because our x is going to cancel on this side, we can subtract 3 from both sides. And that's going to make the 3 cancel on this side. So what we get, these lines, they just appear out of nowhere. And for some reason it's not erasing. Okay, hopefully, I don't know why it's not erasing, but hopefully it's clear that that line just appeared. Okay, so what we wind up getting is -5 is equal to x, and that's it. That's all that we have to do. So the bases are the same, we set the exponents equal to each other, and we have our value for x. Really straightforward, okay? Okay, let's take another case where maybe it's not quite as straightforward. So let's take the case where on one side we have a 2 to the 3x, and on the other side we have an 8 to the 2x plus 1. Now in this case there is one way is more efficient than the other, but if you're not as familiar with your bases, okay, then the second way, which maybe isn't quite as efficient, is the better way. So we're going to do this in 2 different ways. So we're going to have a method 1 and a method 2. Okay, so in method 1, what we want is we want the same base. I'm pausing. So if we could get the same base on both sides, then we could set the exponents equal to each other. So what we're asking is, can we express 8 as a base of 2? And we can. 8 is 2 to the 3rd power. So we can express these as the same base. So that's really the question that we're asking. It's not really with, it's more as. And the answer here is yes. Because 8 is the same thing as 2 to the 3rd. Notice this is a power, okay? We're not doing 2 times 4, we're doing 2 to the 3rd power, not multiplying. So what this means is that we can replace the 8 with a 2 cubed. So now we have 2 to the 3x is equal to, and instead of 8, we're going to write 2 to the 3rd. to the 2x plus 1. That's a 3. It comes out so clear on my paper, but not on the screen. It's a 2 to the 3rd. Okay, 2 to the 3rd. So we replace the 8 with the 2 to the 3rd, and now we have an exponent raised to an exponent. So we can multiply these exponents, which means that 3 is going to get distributed to the 2x plus 1. So now what we have here is 2 to the 3x is equal to 2 to the 6x plus 3. Well, now we could go through and we could say, okay, well, the bases are the same, so the exponents are the same. And it's just what we did in the previous problem. 3x is equal to 6x plus 3. And this is a linear equation, okay? So we can move the 6x over to the other side by subtracting it. Subtract 6x on both sides. Okay, so here what we're doing is we're saying the bases are the same, so the exponents are the same. And then we're saying, okay, solve for x. So when we subtract the 6x from both sides, we get a negative 3x is equal to 3. We can divide both sides by a negative 3. And our final answer here is x equals negative 1. And it's okay, an exponent can be negative. There's nothing wrong with that. So if you look at this and we plug it in, we get 3 times negative 1 is negative 3. And then we get negative 2 plus 1 is negative 1. So 2 to the negative 3 is equal to 8 to the negative 1. Sorry, 8 to the 1st. No, sorry. 2 to the negative 3 is equal to 8 to the negative 1. That's correct. Okay. 2 to the negative 3 is 1 over 2 to the 3rd, and 8 to the negative 1 is 1 over 8 to the 1st. So this is actually equal. Okay, so let's take the second method. And the second method is really for somebody who can't spot very quickly that you can express 8 as a base of 2. So most of you will be able to do that, but when we get to other problems, you might not be able to do it so quickly, or you might not be able to express both sides as the same base. So method 2 will always work, whereas method 1 only works under this situation. Okay, so let's take method 2. So the big difference is we don't have to check for this. We don't have to look to see if we can answer that question. Okay, this is the big question. What we're going to do is we're going to take the log of both sides. We're going to solve this in exactly the same way as we solved the previous problems. So here we have log of 2 to the 3x equals log of 8 to the 2x plus 1. And we can do that as long as we're doing it to both sides. It's totally fine. And what this allows us to do is it allows us to take the variables in the exponent and move them out to the front so that we don't have any exponents anymore. purpose of a log is to solve for the exponent. So I want you to be really careful here, okay? What's super, super important is when you move the exponents out to the front, make sure that you put parentheses around them, okay? Order of operations. You have to take this whole exponent and multiply by the log of 8, okay? The whole thing. If you don't put it in parentheses, it's only going to multiply the 1 by the log of 8. So here's what we mean. On this side, you're going to have 3x times the log of 2. And on this side, you're going to put the 2x plus 1 in parentheses times the log of 8. I'll put this in black. I use the different colors to help you differentiate between different steps or different problems. There's a purpose to it. So that's why I'm going to rewrite it. So this becomes log of 2. And this is log of 8. Okay? So if we didn't, for this 2x plus 1, it matters that these parentheses are over here. It's really important because if you don't have parentheses, it's going to do multiplication first, right? Multiplication comes before addition. So this 1 is going to be multiplied by the log of 8, but this 2x will not be multiplied by the log of 8. Here it doesn't matter because it's all multiplication. But here we have to do the addition first. So the parentheses are really important. So this is very important because people forget to do it all the time. You want to make sure that when you move your exponents to the front, you put them in parentheses. Super, super important. So here, our first step is to take the log of both sides. Then the exponent moves out to the front. Okay, now what we're going to do is we want to solve this. So we're going to divide both sides by one of the logs. It doesn't matter which one, okay? So we can divide both sides by the log of 2, or we can divide both sides by log of 8. So let's just divide by log of 2. It does not matter. Okay, that goes away. And what we're left with is 3x is equal to 2x plus 1. And now we're going to calculate the log of 8 over the log of 2. So 8 log divided by, and again we put in parentheses, 2 log, equals 3. And if you get a whole number here, it's likely that you could have used method 1, okay? So this would be indicative that, hey, yes, I can express both sides as the same base because we got an integer here, okay? So this is times 3. So what we did is we divided both sides by one of the logs. So this is our 1. Our 2 was to move the exponents. And our 3 was to divide both sides by one of the logs. step is going to be distribute, because we have to distribute that 3 so that then we could solve for x. So it's a 5-step problem. So this is what's happening. The 3 is going to get distributed here, because then what we're going to wind up with is a nice simple linear equation. So we get 3x is equal to 6x plus 3. And notice that is exactly what we got up here, okay? So we solve for x. We subtract 6x from both sides. This is just a repeat. That gives us the negative 3x equals 3. Divide both sides by negative 3, and we get x equals negative 1. So same thing as above. And you can see this method is longer. Okay, it's not as nice a method. But it does always work, whereas this one, it doesn't. So it's kind of like in quadratics, the factoring is much simpler in a lot of cases, but it doesn't always work, okay? And you do something like completing the square, which could on occasion be a much longer process, but it does always work. Quadratic formula can be a much longer process, but it does always work. Here, it only works, this method 1, only works when we can express both sides. It's the same base. So let's take another example. Okay, we're going to take 2 more examples. One in which we'll actually do 3 more examples of this. Okay. In the next one, let's say that we have Let's say that we have 9 to the 6x plus 1 is equal to 27 to the 8x minus 2. Okay, so we have to ask ourselves again, can we express 9 and 27 as the same base? Okay, and here the answer is yes, because they're both powers of 3. So notice we're not asking ourselves, is 27 a multiple of 9? Multiples don't matter. We're saying, are they powers of the same number? So 9 is equal to 3 squared, and 27 is equal to 3 cubed. So we're not looking at multiples, okay? We're looking at powers. So now what that means is that we can rewrite 9 as 3 squared, and we can rewrite 27 as 3 cubed. So it becomes 3 squared to the 6x plus 1, and 3 cubed to the 8x minus 2. Okay, then we're going to distribute the 2, and we're going to distribute the 3. Okay, this is an exponent raised to an exponent, so we multiply. So what we get is 3 to the 12x plus 2, and 3 to the 24x minus 6. Okay, you're multiplying the 2 times the 6x, that gives you the 12x, and 2 times 1 is 2. 3 times 8x is 24x, and 3 times -2 is -6. Okay? So you're distributing the exponents. Exponent raised to an exponent, you multiply. And then you can set the exponents equal to each other because the bases are the same. You cannot do this unless the bases are the same. So now we have a nice, neat linear equation. 12x plus 2 is equal to 24x minus 6. We can solve this equation. So we can subtract 12x from both sides. That moves it over to the right side. And then our x is on the right, so we're going to move our 6 by adding it to both sides. We're going to move that to the left. And that gives us 8 is equal to 12x. Divide both sides by 12. Okay, and our final answer . You can divide both sides by 4, so our final answer is 2/3. Okay, so always remember to reduce your fractions. Okay, we're not going to do method 2 for this one because method 1 is more efficient in this case, and you're going to see method 2 in the next 2 problems. So my suggestion is if you want to do a little bit of practice with method 2, you stop the tape, you do it, you see it, and you make sure that you get x equals 2/3. If you don't get x equals 2/3, then you know that you made a mistake, and go back to problem 2 and then our next 2 problems, which we're going to do, and use those to sort of help guide you. Okay? So let's take 2 more problems. So the next one, we're going to do 4 to the 2x minus 1 is equal to 6 to the 4x minus 3. Okay, so in this one, again, we can ask ourselves, can we express 4 and 6 with the same base? And the answer is no. So we have to use the second method. So 4 and 6 are both multiples of 2. They are not powers of 2. So we cannot do this using the first method, okay? So we have to use the second method, which means that we have to take the log of both sides. So we take the log of 4 to the 2x minus 1. We take the log of 6 to the 4x minus 3. And we're going to move those exponents out to the front. So our first step is to take the log of both sides. second step is going to be to move the exponents to the front. Remember to use parentheses. So we have 2x minus 1 in parentheses, log of 4 is equal to 4x minus 3 in parentheses, log of 6. Our next step is to divide both sides by one of the logs. It doesn't matter which one, okay? I would just do whichever one might be easier to do multiplication with in the end. It doesn't matter. So I'm going to divide both sides by log of 6. Just because then on this side, I'm multiplying by 2 and a 1 instead of by 4 and a 3 on this side. That would be the only reason for doing it. So we're going to calculate log of 4 over log of 6. So on this one, we have to type in the 4 first, then press log, divided by, in parentheses, 6, press log, close parentheses, and we get 0.77. I would even go to 0.774 if you want. You don't have to do this whole number, obviously, but you must do at least to the nearest hundredth, because otherwise you have a rounding error. If you did just 0.8, for example, you would have a huge rounding error, and your answer would be so different than what it should be, because you're essentially multiplying by this rounding error over and over again. So round to at least the nearest hundredth, okay? So we said that it was 0.77? Yes, 0.77. So now we have 2x minus 1 times 0.77. You could put the 0.77 here or on the other side, but it's multiplication, is equal to 4x minus 3. So our next step is to do the distribution, to distribute. We have enough room on this page. So you're going to distribute and solve for x. These are always our steps for this problem. Okay, it never changes. It's always take the log of both sides, move the exponents to the front, divide by one of the logs, distribute, solve for x. That's always going to be the case. So we're going to distribute this 0.77. We're going to get, I think, 1.54. And you can even just, on your calculators, because this is always already here, you can even just multiply by 2 here, and then you don't have the rounding error that we have here. Because, for example, if we went as far out as this, and we multiply by 2, you can see it's not really 1.54, it's 1.547, okay? But it's, the rounding error is not as big as if we did 0.8 times 2, which is 1.6, right? That's a much bigger rounding error. So let's use the 1.54. We have 1.54x minus 0.77 is equal to 4x minus 3. Okay, now we can solve. So we're going to subtract 1.54x from both sides. And we're going to add 3 to both sides. That's going to get our variables on the right and our numbers on the left. So what we have here is -0.77 plus 3. I'm using the calculator just because I want to make sure I don't make any mistakes. Sometimes it's been a long day. So on this calculator, you type in the number first, and then you put the plus or minus, so -0.77 plus 3 is equal to 2.23. And then 4 minus 1.54 is 2.46x. So here we can divide both sides by 2.46. To get x by itself. So 2.23 divided by 2.46. And we get x equals 0.91. And that's our final answer there. Okay. Okay, let's do one last one. And it's not really any different. It's exactly the same as what we've been doing. This is the last one that's purely exponential. So we're going to do e to the 2x minus 3 is equal to 5 to the 3x minus 4. Now we've been taking, clearly e and 5 can't be expressed as the same base. E is irrational, so there's no way that it could be expressed as the same base as 5. So we have to use method 2 here. Now the difference is that we've been taking the log of both sides, but here we have e as a base. So it's actually just as good. It's actually just as good to take the ln of both sides here. And you'll see why that's a good way to do this, okay? So we're going to take the ln of both sides. And again, the reason why we're taking the ln of both sides is because we have an e. You'll see why that's such a good thing. Can take the log of both sides. That's absolutely fine. So you can always take the ln of both sides. We've been saying take the log of both sides, but you can take the ln of both sides too. The reason why we've been doing the log of both sides is just, I don't know, personal preference. But you can do either one, because in each case, okay, we can put it into our calculator. So it really makes no difference. Okay? So we're going to do the ln of e to the 2x minus 3. equal to ln 5 to the 3x minus 4. And then we can bring these exponents out to the front just like we did before. And the reason why we would take the ln of e is because the ln of e is equal to 1, okay? What we're doing is we're saying log base a of a is 1. So the reason for this is that we're saying a to the first, if we put this in exponential form, a to the first is equal to a. Right? We're saying a to what power is equal to a, and this is true. This is the same thing as saying log base e of e is equal to 1, and that's true. E to the first is equal to e. Okay, so we're just using this basic property here. So the ln of e is the same thing as log base e of e, and log, if the argument is the same as the base, then the log is equal to 1. Okay, because when you raise anything to the first power, you get itself back. So we're going to use that, and what that means is that this is just 2x minus 3 equals 3x minus 4 times the ln of 5. So you don't have to rewrite this. I'm going to rewrite it here, but you don't have to. I'm rewriting it just so that you know that we're just saying that the ln of e is equal to 1. But you absolutely don't have to. So now we could go in and we could compute the ln of 5. So we type in 5, and then we're using ln now, so it's ln of 5. So we get 1.61. It's not that it saves us so much, it just saves us a few little things of typing, okay? It doesn't save us that much, but some of you may feel it saves you enough, or it looks neater, so it's worth taking the ln of both sides, okay? So now we're going to distribute this 1.61 to the 3x and to the 4, and when we distribute that, times 3 is equal to 4.83, and 1.61 times 4 is equal to 6.44. And this is equal to 2x minus 3. So now this is just solving a linear equation. We're going back to that solution where we move the axis over to one side. So to keep the x's positive, we're going to move them to the right, but it doesn't really matter. That means that the numbers are going to be moved to the left. .44 cancels, the 2x cancels, and what we're left with is 3.44 on this side and 2.83x on this side. We're going to divide both sides by 2.83. And 3.44 divided by 2.83 gives us 1.22. What did we say, 1.22? Yes, 1.22. And this is our final answer. So same thing, it doesn't matter if you take the ln of both sides or the log of both sides. If you had taken the log of both sides, you just would have had to find the log of e. So here's E on your calculator. You would just press E. Some calculators, it automatically puts a caret, and you would have to type in E to the first, and then you would put in ln, and you could see that the ln of E is just 1. Okay. Okay, so after this, there's one more video lecture. That last video lecture is just going to be the last set of equations with logs.